Okay, so the last lecture we looked at allyl chemistry, and in particular we looked at the molecular orbital picture for systems that contain more than 2 pi electrons. We could draw the MO diagram for allyl species, for butadienyl species, and I've given you guys an assignment to try one for the pentadienyl. I'm not going to complete that one now. I'm going to let you guys try it on your own, and then we look at it on Wednesday. There are a few reactions of allyl species that are of interest, and among those is allyl halogenation. Right? Allyl halogenation. And this reaction is rather useful. And essentially in this reaction what we're doing is we will take an allyl species and treat it with one of 2 reagents. We can use chlorine and light or bromine and light. And bromine is actually slightly better because of the greater selectivity. So I can use bromine and light. Or I can use a reagent called NBS. NBS is an acronym for N-bromosuccinimide. It's N-bromosuccinimide, which essentially looks like this. Okay, so that's N-bromosuccinimide. And if I treat the allyl compound, in this case the propene, with N-bromosuccinimide or bromine in light, what I get is this product. In other words, I get allylic bromination. Now I could carry out the reaction with an excess of bromine and get the dibromo and the tribromo species, but I could limit it to making the monobromo species. What's important in this reaction is to recognize the specificities, because it means if I take propene and I treat propene with bromine in, say, carbon tet or methylene chloride, what I would get would be the 1,2-dibromo propane. And this essentially is an addition reaction involving charged particles. So we make the bromonium ion that gets attacked by bromides. We're doing ionic chemistry, which leads to the overall addition. So this is ionic addition, right, of bromine to the alkene. But if I use the same bromine, but this time do it under free radical conditions, so say bromine in light, or, as we said, NBS, what you generate is the allyl bromide. And this, in fact, is essentially free radical substitution. And it's really kind of interesting that you can use exactly the same reagents, bromine and the alkene, and if you change the conditions, you get 2 entirely different reaction mechanisms. You get the 1,2-dibromo species by ionic addition, or you can get the allylic species by free radical substitution. I know you're familiar with how bromine itself undergoes fracture in the presence of light, it undergoes homolysis in the presence of light to generate the bromine radical. And it turns out that NBS does exactly the same thing. If you take NBS and you simply warm it, then that species simply undergoes a free radical process because the NBr bond is somewhat labile. And what you generate then in both cases is Br dot. And then Br dot attacks the alkene at the allylic position. And why is that? Because if it attacks the allylic position, it gives rise to the more stable allyl radical. So the Br dot attacks the allyl position, gives rise to the allylic radical, which of course is resonance stabilized. That's the point we made earlier, that any intermediate you make in the allyl position is very stable. So you end up with a species that is resonance stabilized, and then that allyl species turns around and attacks more of the species. So if I was doing the reaction with bromine, then this would attack bromine. and I'd make my allyl bromide. Or if we were, oh, for heaven's sake, if we were working with NBS, then this would attack NBS, and we would get chemistry, right? We would get our product. So allylic bromination is a particularly useful reaction because it allows us, it gives us the option of functionalizing an alkene with bromine, but choosing to do chemistry either at the vinylic site or at the adjacent allylic site. In fact, there's a very popular question that shows up on very many exams, which is, how would you convert this compound, which is in this case propene, into 1,2,3 tribromopropane? Right? How would I make that compound? And you know, the way you do it, I'm going to get the hang of this eventually. The way you do it is you take advantage, first of all, of the allylic chemistry of the species. Because, of course, if you simply went ahead and added bromine first, well, then I would add bromine across the double bond, but I would lose the ability to put the next bromine on this side. So what I would do is I would take advantage of the allylic chemistry and treat this as NBS. I'm sorry, excuse me. And that's going to give rise to the allyl bromide. And then treat the allyl bromide with bromine in carbon tet, and I will add to the carbon-carbon double bond and make my product. And that is a successful method of making the 1,2,3 tribromo species. And you know, if we were being clever, we would ask you, how would you convert the propene into glycerol, right? Which is 1,2,3, the trihydroxy species. And the answer is I'm simply going to do SN2 chemistry, 3 molar hydroxide, cold, so I'm going to do SN chemistry, and I'll make the triol. So this is a pretty useful way of tri-functionalizing at both the vinylic and at the allylic position. Alright, so this would conclude the study of allyl chemistry. And the most important thing about it was the allylic halogenation and an introduction into the molecular orbital picture of species that contain more than 2 pi electrons. That in particular will become important when we start looking at ultraviolet visible spectroscopy. So what we'll do now is we look at the chemistry of dienes. Okay, the chemistry of dienes. And I forgot to time myself here. So I guess we'll classify dienes, and we can do that in one of 3 ways. Dienes can be classified as either isolated dienes, and an isolated diene is one in which the proximal vinylic carbons, in other words, the proximal vinylic carbons are the inner vinylic carbons, the ones that are close to each other. So this one and this one are the proximal vinylic carbons. Isolated dienes are species in which the proximal vinylic carbons are separated by at least one sp3 hybridized carbon, or by at least 2 sigma bonds. An isolated diene is one in which the proximal vinylic carbons are separated by at least one sp3 hybridized carbon, or by at least 2 sigma bonds. They're called isolated because chemistry happening at one site, one vinylic carbon, is completely unaffected, and in fact unaware of the chemistry happening at the other site. So I could go ahead and I could add HBr to this site, and this site will never know, right, and never participates in the chemistry. There's another class of dienes which are called cumulated dienes. Cumulated dienes. Cumulated dienes are also called allenes. And you've actually seen these already. A cumulated diene is one in which I have a dienyl entity, but the geometry is such that one terminal vinylic carbon is in the plane, say, of the board, and the other one is perpendicular to that plane. And if you look at the cumulated diene, what you have, in fact, is two terminal sp2 hybridized carbons and one central sp hybridized carbon. The last class is the conjugated diene. And the conjugated dienes are those species in which the proximal phenylic carbons are separated by only one sigma bond. So in fact, I guess one of the better ways of doing it would be to say, isolated, the proximal phenylic carbons are separated by at least two sigma bonds. Conjugated, the proximal phenylic carbons are separated by one sigma bond. Now, I couldn't say for cumulated, the proximal phenylic carbons are separated by no sigma bonds, because in reality, that's not quite true, but I'm going from this scenario to this one, and then finally to this in the allele. We will spend a lot of time talking about the conjugated dienes. Isolated dienes behave very much as normal alkenes. So all the chemistry you've seen for alkenes goes exactly the same way if they were isolated. It's just that you would do it twice if you had enough reagent. The allenes are an interesting class of compounds, and they have a wealth of chemistry, but it's not normally studied in intraorganic chemistry, except for one aspect. And this is just a reminder of something you'd have met in 301, and that is they are a good illustration that you do not need to have a stereocenter to be chiral. And that as long as your allene has two different groups on any one of the carbons, the allene will be chiral. So, for example, if I put, in fact, I'm gonna redraw this at the bottom because I need a bit more room. If I take my allene, let's get a bit more room here, and I draw it like this. Alright, so these two carbons in the plane of the board. Let's say I put some group A and B here, and I put, I guess, A and B here. There's a mirror plane, which will give me this species, right? I'll have C, double bond C, double bond C, A, and B. And then I'll have A behind the board and B in front of the board. If I took the species on the left, on the right, and I moved it across the mirror so that this A is on that one and this B is on that, and then I rotate it 180 degrees, what I will find is that the back B would fall on the back A, and that the front the front B here would fall on the back A, and the back A would fall on the front B, so that they no longer superpose. So even though these two superpose perfectly, right, this A and that A, and this B and that B superpose perfectly, this and that will fall in each other. And so what it means is, I have a species whose mirror image is not superposable upon it. In other words, these species are chiral. One of them will rotate plane polarized light clockwise, one will rotate plane polarized light anti-clockwise. Okay? And really only concerned with allenes at this level, only because they illustrate that we do not need to have a stereocenter in order to be chiral. Okay. So we're going to look at the chemistry of the conjugated dienes. And there are two reactions of conjugated dienes that we are interested in. Okay? So these are reactions of conjugated dienes. One is called polar addition. And if, for example, I'm just going to recap, let's say I took propene again, and I treat propene with 8Cl. Right? What happens? And the answer is, well, I'm going to end up with a single product, which is 2-chloropropene. And you remember this because what essentially happens is the alkene is nucleophilic, or if you want, basic, it will attack HCl, and I'll break the HCl bond, and that's going to generate this species. So that's a base reaction. I'm going to generate one of two species. I could, in theory, generate the primary carbocation. In other words, if the H went to the secondary carbon, I could make the primary carbocation. Or I could put the H on the primary carbon, and I would make the secondary carbocation. We know that primary carbocations, unless they're resonance stabilized, are not accessible. And so the only cation I will get will be the secondary one. So this secondary carbocation is then scavenged by chloride, right? And that gives rise to 2-chloropropane. So we end up with a reaction that is regiospecific, right? This is a term you remember from previous lectures. It's regiospecific because we end up getting the H and the Cl in a specific region of the molecule. Okay? That, of course, is different from being regioselective. Just to remind you, if I started off with this alkene and I treat that with HCl, I would get two products. I would get this one, and I would get this one. This would be major, right? Because it goes via the tertiary carbocation. I'd get this one as a minor because it goes via the secondary, but I'll get them both because I can make both secondary and tertiary carbocations. This reaction shows regioselectivity. This is a regioselective reaction, meaning that I'll get more of one than the other, but I'm going to get them both. Specificity means I only get one. Two are theoretically possible, but I only get one. But the point is that if I treat an alkene with HCl, there's a protocol that's followed. The alkene attacks the H, makes the carbocation, most stable one when it can, and then the chloride attacks the positive site to make the product. Well, what happens if I treat a diene with HCl? So let's start with butadiene. And you guys might remember this is called 1,3-butadiene, and we looked at it in terms of its molecular orbital picture in the last lecture. So what happens when I treat 1,3-butadiene with HCl? Well, let's see. You might expect that the diene would attack HCl. Of course it would, because the alkene is electron-rich. This is nothing different from what we just saw a second ago. Right? The alkene is electron-rich, and so it attacks the HCl. The sigma bond breaks, and I'm going to make the carbocation. And I have the option of making either primary carbocation, which I avoid, or making the more stable secondary carbocation. So the same thing happens here. The alkene, the diene attacks the, the diene attacks the HCl, and I have the choice of making either a primary carbocation by putting the H on this carbon, or of making a secondary carbocation by putting the H on this carbon. And much in the same way, we know we can't make the primary carbocation, so this route is not followed. In other words, I see specificity in terms of where the H goes. The problem is, this secondary carbocation is secondary and allylic. Right? Remember, allyl positions are pretty stable. That allylic cation, therefore, is one of two resonance forms, the other one being this. And you might say, well, geez, I made a primary carbocation after all. The answer is, yeah, but this is primary and allylic. And allyl cations are roughly as stable, in fact, many are actually more stable than tertiary carbocations. And of course they are, because resonance stabilization vastly outstrips inductive stabilization. So even though I'm a primary carbocation, it is allylic, and therefore I can form it because it is resonance stabilized. In other words, the true species then is a hybrid which looks like this. I'll have my H here, and I'll have my positive charge be localized between this carbon and that carbon. And I'm going to go ahead and number those carbons. I'm going to say that the position in which the first carbon, the first H went, I'm going to call this carbon number 1. Right? So I'm going to say that my positive charge is delocalized between carbon 2, 3, and 4. And in fact, I'm going to have significant positive dipoles on carbon number 2. This is carbon 1, 2, 3, and 4. So carbons 2 and 4 will have a positive dipole. Right? Carbons 2 and 4 are going to have a positive dipole. Carbons 2 and 4 are going to have a positive dipole. Okay, well, what is the next step if this were a reaction of propene with chlorine, with HCl? And the answer is, once I've made my carbocation, chloride attacks the positive site, and we end up with the substitution product. Okay? Well, I guess the same thing should happen here. So chloride will then attack the species to make the haloalkane. The problem is, there are now two targets. Because the positive charge is not centered in carbon 2, it's not centered in carbon 4. When the chloride looks for a target, it sees both carbon number 2 and carbon number 4 as being positive, and so it attacks them both. If the chloride attacks at C2, what I'll end up with will be this compound. If the chloride attacks the resonance stabilized carbocation at carbon number 4, what I'll end up with will be this compound. So this will be attack at C4. So in reality then, I actually get two products from this reaction. I get what's called the 1,2 product, or sometimes called the 1,2 addition product. It's also called the simple product. It's also called the simple product. And it's called a simple product because it is the one you would have expected to form. I mean, if I told you before this discussion that I had a diene and I was adding HCl to it, you would tell me, well, quite simply, I'm going to put an H in this carbon and a Cl in that carbon. The H would go here so that my plus charge ends up being secondary, and then the Cl minus just collapses into it, gives me that. So the simple-minded product is the one you'd expect, which would be this one. I would call this species the 1,4 product, or sometimes the 1,4 addition product. Right, so it's a 1,4 product. And it's not called the difficult product, it's called the conjugate addition product. Right, so it's called the conjugate product or the conjugate addition product. And it's called that because the fact that we can get attack at Cl at carbon number 4 arises because the positive charge is in resonance. In other words, I've got conjugation, and I've got conjugation between C2 and C4, right? So this resonance interaction is called conjugation. And what the conjugation does is it smears the positive charge between C2 and C4. And so the 1,4 product is called the product or the conjugate product. Well, here comes the question. Which one do I get? And we already answered that, we get them both. But which one do I get more of? Do I get more of the 1,2 product? Do I get more of the 1,4 product? And can I adjust my reaction conditions to get a preponderance of, say, the 1,4? Can I adjust my reaction conditions to get a preponderance of the 1,2 product? Right? How can I manipulate my conditions to get more of one than the other? And the answer lies in understanding the details of the reaction between the chloride and the carbocation, because that's where the decision as to which species we get is made. Right? The first step of the reaction, the protonation, that's fairly straightforward. Okay? But in forming the product, it is the reaction of the resonance stabilized carbocation with the chloride that determines the product distribution. So let's investigate then this carbocation in a bit more detail. If you notice how I drew it just above here, right? I sort of drew it in a very non-detailed fashion, simply saying that the positive charge is delocalized over C2, C3, and C4, with the plus charge being on C2 and C4. But in reality, although that's true, is the dipole on C2 exactly the same as the dipole on C4? Right? In other words, I could put a delta plus charge here and a delta plus charge here, but is the size of delta exactly the same? And the answer is no. One of these carbons is way more positive than the other. So let's see which one. Let's go back to our resonance forms. When the plus charge is on C2, I really am describing a secondary and allylic carbocation. When the plus charge is on carbon number 1, I'm describing a primary and allylic carbocation. So let's say allylic carbocation is a wash, right? Because there's a certain fundamental stability associated with any allylic species. So that's equivalent, significant and equivalent. Beyond that, this one is secondary, this one is primary. Primary carbocations are more stable, are less stable than secondary carbocations. And therefore, this species is actually more stable, makes a bigger contribution than that species. I could look at it another way. I can say that when I actually have the hybrid, because the secondary position is better able to handle the positive charge, there is a larger positive dipole at carbon number 2 than there is at carbon number 1. So what's the consequence of that? The consequence of that is, if the charge in carbon 2 is greater than the charge in carbon 4, the attack by chloride on carbon number 2 is easier. Right? This is an easier attack than the attack by chloride on carbon number 4. This is more difficult. Right? Right? It's more... Did I really write difficulter? Oh my God. Right? The attack... So the attack is more difficult. Okay. Now, how do we indicate ease of reaction in a reaction profile diagram? So what I'm going to do is I'm going to draw a reaction profile diagram that looks as follows. I'm going to have my reaction coordinate, and I'm going to have energy on the vertical axis. I am going to highlight the energy of my ion pair. This is my carbocation. This is my carbocation and my chloride. Right? Carbocation, my chloride. Attack at C2 is easier than attack at C4. Okay? And what that translates to then is that the activation energy barrier for attack at C4, so this is C4, right? C4, this is, or better yet, let's say the 1,2 product. So this is going to the 1,2 product, and this pathway is leading to the 1,4 product. Right? So this goes to 1,4. Right? So easier means lower activation energy barrier. Okay, that's good. Let's look at the two products now. Right? The product from C2 attack, which is a simple product, is an alkene. It's a chloroalkene. But the double bond is mono-substituted. It's a terminal double bond. The product from attack at C4, on the other hand, is an internal alkene, and its double bond is di-substituted. We know that di-substituted alkenes are more stable than mono, because alkene stability is affected by the degree of alkyl substitution. The vinylic carbons are electron poor, and the more alkyl groups I attach to them, the more I stabilize them. Okay? So what it means is the 1,2 product, which is a simple product, is actually more energetic, less stable, than the 1,4 product. So I can draw this profile diagram like so. Right? This is my 1,4 product, right, which has the stable 1,4 species as the product, right, where the double bond is di-substituted, and this would represent the 1,2 product, where the double bond is terminal. Now, this is particularly interesting because what this means is that the more stable product is forming via the more difficult reaction. And I'm going to say that again. The more stable product is forming via the more difficult reaction. And this is very counter to everything we've met before. And I'll give you an example. In fact, we just looked at one, right? We said propene. When I treat propene with HCl, I had the option of making either the primary carbocation, right? Of making either the primary carbocation, right? By putting the H on this carbon, with a plus V here, or making the secondary carbocation, right? By putting the H on this carbon, so the plus charge goes here. And why do we only make the secondary? The answer is because, well, look, right? Here's my substrate, my propene and HCl, right? Primary carbocations have an energy value up here, which means the activation energy barrier to make them is massive, too large an energy barrier for us to circumvent, and therefore we just don't make primary carbocations. The secondary carbocation has an energy value that is here. Okay? And so the energy required to make it, that is accessible. So the more stable species, in this case a secondary carbocation, forms faster. Okay? And that's typically what we observe, right? The more stable species dominates the product distribution because it is simply formed faster. The same thing is true with alkenes, right? If I had a choice of making either say deprotonating this species, if I were to treat this with base like hydroxide, why do I get more of this compound? Why is this major? Why is this the major product? And this one is minor. And the reason is exactly the same. Because when I'm deprotonating this species, the reaction is actually endothermic. In fact, I can just substitute my entities on this plot. And I can say, well, the reason we get chemistry for one but not the other is if I start off with this compound, right, so this is my bromine and hydroxide, that's my starting material, the tri-substituted alkene happens to be here. The mono happens to be here. Right? And therefore, by the Hammond-Leffler postulate, since reaction is endothermic, I would make the more stable species faster. And therefore, there will be more of it in the product distribution. So, our experience so far has been that the more stable thing forms faster. That is not true in this case. The more stable product forms via the more difficult reaction pathway. Okay? And there is a term we're going to use for this kind of event. We say the reaction is an issue of kinetic versus thermodynamic control. Versus thermodynamic control of a reaction. Right? So kinetics controls the formation of the 1,2 product because it's formed faster. Thermodynamics, stability, controls the formation of the 1,4 product because it's more stable. So in fact, we can actually get other names for the 1,2 or the simple product. This will be called the kinetic product. It's called a kinetic product or the product under kinetic control. So I can call it the 1,2 product, the simple product, the kinetic product, or the product under kinetic control. Similarly, I can call this one, the 1,4 species, either the 1,4 product, the conjugate addition product, the thermodynamic product, or the product under thermodynamic control. Right? It's a thermodynamic product, or the product under thermodynamic control. We'll pick up on this some more when we go to the next lecture.